Hi, my name is Selassie Dumeno and my partner is Jordan Stevens. This is our presentation 6 for ENGI 305. So here's a quick overview. We're going to look at the time series data, parts of a forecasting equation, some smoothing model methods, and then the ARIMA model. So basically, time series data typically exhibits predictive patterns, and these patterns can be modeled by using forecasting techniques. Some of those techniques are smoothing methods and ARIMA. And for smoothing methods, we have simple, we have some exponential, and then we have winters. So if we want to look at some parts of a forecasting equation, we have trend, which basically deals with trying to detect long-term movement. And then you can detect this by using a line fitting with the slope. Cycle is also a part of a forecasting equation that's for multiple year oscillations with a frequency, and that can be modeled using lag periods. And then for seasonal, we have within year oscillations, and then irregular error, which deals more with random movement that does not have an identifiable source. Okay, so looking at smoothing methods into detail, it basically refers to the neutralizing of the random irregular components. Simplest smoothing technique is the moving average, and that is basically when a certain amount of observations closest to the current are averaged in order to predict the next value. Exponential smoothing is a type of smoothing, and that's very similar to the simple one, but it uses an exponential equation to weight the closer values to have more of an effect on the next value. Holtz is another method which expands on exponential smoothing by accounting for the trend. And then the Winters method is also another one, and that expands the forecasting method to include seasonality with an additive and multiplicative model. So basically it starts from the simple, and as not necessarily as it gets complex, but with every step down, it builds on the other model while incorporating something new into it. And then when we go over to ARIMA basically stands for autoregressive integrated moving average. And that needs a stationary model to work properly, but the Box-Jenkins approach can be used to difference the time series data with a trend into time series data with no trend. And then ARIMA technically has three parameters: the P, D, and the Q. P is your autoregressive order, and that typically refers to your lag period for the model. D is your differencing order, the number of differences to make the data stationary, and then for Q is your moving average, and that's the number of lag value to include in the model. So basically for this, we're going to go over to jump now, and then the data that we're going to be using is the India industrial production data. So over to jump, we're going to be using the India industrial production to demonstrate our exponential models, our trend analysis, and our ARIMA models. So first, for our smoothing models, we're going to go to analyze. We first need our time series forecast, so we go to modeling, and then if you click on time series, then we're going to make our basic goods our response, and then we're going to do that by month. One thing we're going to do is we're going to change our auto correlation lags and forecast periods 3. Click OK. So it gives us our time series model right here. And as you can see, gives us our mean, our standard deviation, the number of points. But what we want to do is we want to check the smoothing models. So we click on the red arrow. And then as you can see, when you come down here, you see all the smoothing models. So if we want to start with our simple exponential model, smoothing model, click on that. And if we let's say our confidence interval is 0.95, then we just go from 0 to 1, and then we estimate. And then you see that it gives us our smoothing model. If we want to see it, we can click on the graph, so it will show us exactly what that looks like. So the red shows us our models. When we check our numbers, the one thing that we can come and check to see how good the model is, we check our R-squared value, and we see that this is 0.93, which tells us that this is a very good model because, again, with the R-squared value, we want to go as close to 1 as possible. I will go ahead and then show you a couple other models. So if we go back to smoothing, the cool thing about jump is that it stores all the models. So if we go and do a linear exponential smoothing model right here, again, if we keep our confidence interval at 0.95, 0 to 1, as you can see, if I take off the simple exponential and I put in the linear or the Holtz, it shows us right here. And then once again, always to test for a goodness of fit, you can go all the way down. And as you can see, this is the whole exponential smoothing. And when you check your R-square value, similar gave us a 0.93. I think I'll do one more. Go in here. And then let's just do a Winters method. With the Winters method, you see we have an extra column here, which is the periods per season. And we're going to go with 12. Let's just say 12 months. And then we're going to keep our confidence interval at 0.95 and when we estimate. See how that comes in blue. So when we do that, we see a better representation of our Winters method. And once again, that is additive. As you can see here, it states that it's additive. And this is basically how to generate your smoothing models in Jump. Okay, so next I'm going to show how we can generate some trend analysis. And we're once again going to be using the India industrial production. So for this one, we're not going to do anything in modeling necessarily. We're just going to use a fit y by x, which will examine the relationship between two models. And then for this one, we're just going to have our x factor be our months, and our response once again be our basic goods. When I run this, you'll see a bivariate fit, the basic goods by month. Go ahead and blow this up. So I'm going to try and fit the line. When I fit this line, we look at this. When we look at our basic goods, our linear fit, we see that our slope is basically 0.89 or 0.9, and our R-square value is 0.9, basically 0.92. It tells us that this is a really good model. But we can go a step further with this and then try and create a log linear model. And for that, we're going to have to fit the polynomial and do a 2 quadratic. And when we do this, if you notice the difference here, with just the linear model, or just the linear just running the linear fit, we see that our R-square value is 0.92. But when we use the polynomial fit with a degree of 2, see that R-square value increases to 9.4. So what that tells us is that the polynomial is probably a better fit for analyzing the trend of the data here. When we go down again, another thing we can check on is our root mean squared error. And then the linear fit shows a 8.69. And then the polynomial should predict a drop. If I'm not wrong, polynomial should predict that it should drop. And yes, as you can see, this is 7.19, which is lower than the linear fit. So sometimes when you run a linear fit, although it might be a good enough fit, you can try your polynomial just to see if you can get a more accurate representation of your data, which will in turn improve your forecast. Alright, so now I'm going to show you how to create some autoregressive models, basically ARIMA models. But we're not going to go through the whole steps of generating our time series because we still have our smoothing exponential model data over here. And that time series that we generated from that is what I'm basically going to use to show you. Okay, so if we go in here, as you can see, we have our ARIMA right here. And let's say we want to create our ARIMA model. We need a P, a D, and a Q, and our P is our autoregressive order. Our D is our differencing order, and then our Q is a moving average order. So if we wanted to create a PDQ of basically 1, 0, 0, all we're going to do is put our P will have a number 1, or will be 1, our differencing order will be 0, average order will be 0. When we estimate that, and then we try and graph it, so we put it in here, and then when we try and graph it, it should show us what that looks like. Again, we can jump is pretty cool because you can compare smoothing exponential models with ARIMA models. And then we're going to go ahead and check our R-squared value. Go down here. In our model AR1, check our R-squared value. We have an R-squared value of 0.88, which is a decent model. It shows us our residual ACF and then our residual PACF. So let's say if we wanted to compare between models now, let's say we want to compare our linear Holtz to our AR, all we have to do, and then it also sections everything out, assigns it its colors. So let's say if we section this out, you can clearly compare and contrast between the models, which again is pretty cool. Saves you a lot of time instead of switching between models manually and trying to see or detect whatever changes that might be in there.